A modern data center consumes hundreds of kilowatts of electricity to predict the next word in a sequence. By contrast, a peregrine falcon intercepts prey at speeds of 240 miles per hour while running on exactly 1 watt of metabolic power. The industry currently equates intelligence with the size of a data center, but winning the intelligence race requires a shift toward the right mathematical equation. AI pioneer Yann LeCun argues that current systems conflate fluent text prediction with true agency. Genuine agency is the ability of an autonomous system to persist in its goals across different contexts. This chart lists LeCun's 4 foundational criteria for a machine agent: world grounding, persistent memory, causal planning, and controllable safety. Large language models fail these tests because their internal models are statistically correlated rather than anchored in physical reality. These systems produce fluent text without a sensory link to the world, leaving them unable to verify their own outputs against external facts. While we expect machines to execute functions with deterministic precision, large language models produce tangled outputs. These models operate as statistical manifolds, mathematical maps that connect data points that are disconnected from verifiable truth. This grid is the topological trap. AI maps text to text in a fixed geometry, disconnected from reality. This intrinsic curvature cannot be perfectly flattened. Applying an RLHF safety filter simply redistributes the mathematical strain. Suppressing one hallucination guarantees a new failure elsewhere. This effect, known as Dirichlet strain energy, acts like a squeezed balloon. Flattening the surface in one area causes an immediate, uncontrollable bulge to expand elsewhere. These hallucinations are mathematical inevitabilities of the system's current architecture, rather than simple software bugs. Biological organisms solve complex navigation and survival problems without large-scale neural networks. They achieve this by constantly adjusting their path based on environmental feedback. Nature's blueprint relies on gap closure. When a planarian flatworm is cut, its cells measure the physical discrepancy between their current state and a stored bioelectric target state. Intelligence is the continuous action taken to reduce that gap. The semiotic web implements this biological flow by replacing standard text prediction with an architecture designed to close gaps between predictions and reality. The system uses a tokum as its atomic unit of meaning, a cryptographically locked, executable data structure. It links a pure abstract concept, or CCI, to a grounded real-world measurement, the CTI. A third node, the provenance, provides an auditable cryptographic history. Because altering any single component invalidates the hash, the tokum structurally dissolves if its data cannot be verified. This makes unverified reasoning impossible. The peregrine falcon follows the agapistic cycle, using continuous sensory reality checks to override its internal predictions every millisecond. In the final stage, convergence, the falcon completes its action only when the physical gap between itself and its target hits absolute zero. Today's AI assigns a probability to a dangerous action, applying a safety filter that can be bypassed. In contrast, the semiotic web utilizes structurally bounded refusal. Without a verified cryptographic hash, the mathematical pathway physically ceases to exist, and the agent halts. This architecture prevents an agent from being tricked into a fake output, because the logic will not resolve without grounded, verified data. We can see this architecture in action through the case of a patient named Marie. Marie's data is managed by a halonic federation. This layered model includes a global cloud for concept definitions, localized hospital networks for verified procedures, and private edge portals for individual users. When Marie's smartwatch detects a glucose spike, it processes the data locally. Her private portal maintains absolute data sovereignty. The measurement is cryptographically signed and shared with the hospital's network for diagnosis. Her private data never hits a centralized cloud. This decentralized structure secures user data while allowing for precise, real-time medical agency across a network. When evaluating treatments, the AI encounters a structural refusal for a rare genetic condition. The required hash is missing, so it refuses to guess. Instead, using causal due calculus, it identifies a type 2 diabetes treatment, selecting a path based on verified historical trajectories. This grid visualizes semantic gravity. When an agent verifies a prediction against external reality, it deposits mass into the network. Highly trusted facts become gravity wells that curve semantic spacetime, making it computationally cheaper to reason using verified truth than to hallucinate. This table summarizes the shift. We are moving from centralized clouds and probabilistic correlation to a distributed edge architecture using causal reasoning and immutable cryptographic ledgers. The 21st century requires an infrastructure where machines verify reality through semantic gravity, shifting the focus from text prediction to the pursuit of grounded knowledge.